Morning.
What does that say?
Oh, okay as is, because you corrected it, but it being 7 was okay.
Oh, okay.
Are you in it too? Yeah, it's like, don't use the commas improperly. The essays are like 500 two essays. So as long as you do a short essay. Because then you count two chapters on the last.
My favorite part was always the wildlife. Wildlife and forestry.
I mean, it was. I think those calculations are actually
Oh, like when it's D of X or D of Y? Yeah, because I think you just have to label when it's being mixed up with D of X.
not be straight, bro.
None. Oh, you're pretty bad. Like this last one.
All right. Are there any questions before we get started? And then, so don't forget, I did make an announcement about that Stanford Community College transfer thing, so check that out. Go to it. It's tomorrow. I want to say at 3, so it might be some good information. Any other questions or that we need to talk about? All right, so let's do some demos then, because we are kind of set up, and this will lead us into acids in solution here. And so now we have to think back to ionic compounds for a second. And then, except we made the distinction, right? So we kind of have, and let's just say in our like reactions, for example, right, if we have sodium chloride, we usually denote whether it's in solution, so AQ. And so let's kind of look at that distinction and what we're showing there, what's the difference, what's going on. And so kind of the first thing that we talked about with ionic compounds is that the solid itself does not conduct electricity. And so let's just kind of verify this. So we have salt up here. Oh, is my camera not firing? I think I don't have enough power with this crappy laptop. And it is struggling. Come on. Are you alive? Oh my gosh. Okay, let's see if it works. Okay, it's still functioning. Nobody. And so I have it hooked in. We have our light bulb. And so in here we have kind of to complete the circuit. So obviously, right, you wouldn't want to do that. That'd be a safety hazard. So electricity, runs across your body. You don't want your body to complete the circuit. And so let's put it in there. And okay, nothing happens. But that's what we expect, right? So there's no movement. There's no solution. So it doesn't do anything. Let me wipe this off. I brought my goggles and I forgot to put them on.
Safety first.
Exactly. So safety first. And so now let's do. So now we have sodium chloride pre-made solution. And so let's just pour that. Yeah, so now what happens when it's aqueous? So let's put this on the camera.
Ions can move around.
Yes.
Wow!
Yay. So it lights up nice and bright. And it's right, we see that ions moving around in solution. And that's, oh my gosh. I completed the circuit with myself. That was not a good thing.
What did it feel like?
A little volt. Yeah, you gotta be careful with that.
Tiny taser.
Yeah, although I've never experienced a taser. And so now let's do just distilled water for comparison. And so right, no ions in distilled water. And so we didn't expect it. Oh, so it's a little bit of a glow.
Is that because of the ions that are still on the diodes?
So that's a good question. So I could try to wipe it better without electrocuting myself this time.
Would there be any impurities in the distilled water making it?
So that's the other
So
question.
it's not really distilled water.
Yeah, so distilled water is only so pure. So in our labs, we only use distilled water, so now it's not lighting up, so maybe it was an impurity, so not quite sure. But yes, there's still ions in distilled water, so if you were doing like a really analytical analysis, you were doing ICP chemistry, trying to do metal analysis, you'll be working with like what's called millipore water, or like nanopore water, where they just keep filtering it to get out those ions. And then, so now this brings us to our acids, or let's start with organic. So we mentioned, okay, well the ions, oops.
Whoa!
And so of course, right, the key is, well, we said ionic compounds, why they light up pretty nicely, is that they have, of course, some sort of cation plus anion. And so that could be, right, simple sodium chloride like we've been looking at, so it disassociates. And so what this is, we can also look at it in another way, because we can say, well, if we have sodium chloride, solid, and then we put it in solution, then of course it disassociates. And I'll just put an aside, right? This could also be, let's just do ammonium, phosphate, or any other polyatomic. Any polyatomic ions. So all those, again, say behavior. And so now let's look at an organic molecule. So we're going to look at sugar. And I don't want to draw sugar. That would be painful to watch me draw it. Well, sugar isn't too bad.
Do it the lazy way, just draw a hexagon.
Yeah, but I still suck at even drawing a hexagon. Plus, there's all the little stereochemistry. I don't want to do the stereochemistry. Oops. And so let's look at our sugar here. So there's sugar. So right now it's more of a discrete molecule. And so let's see if we can get it to light up. So first let's just test our dry sugar. Oops, oh my gosh.
Do you want to change the camera for the
Oh, thank
live
you.
stream viewers? Hiccups.
Do. And let me put back on our preview, assuming it's still working.
It's
Okay.
still working.
And so, of course, right, we don't expect it to do anything. So now let's see. I know it's the sugar. So let's pour some in solution. Pour a lot in there. So let's see if we can get. I was wondering if it would light up at all. So nothing. So nothing's happening. So we have an organic molecule. So no ions. And so now let's look at vinegar. Where's my vinegar? I don't think I poured it out. Here's my jar for vinegar. And so let's first write out our formula, sorry. So let's look at what is vinegar. And so COH. So this is vinegar here, our acetic acid. And we'll look at why it's called acetic acid. So those are just carbons, hydrogens. And so let's pour some out. Let me go back to my large cam. Now I see why those podcasters all have producers, do my camera work for me. And so now vinegar, aka acetic acid. So we'll pour that in. And so now let's see what happens. Uh-oh. Maybe I picked too weak of an acetic acid.
What's the dilution of it?
It's 0.5%, which I thought would be enough. Huh? Yeah, if you wouldn't mind. Let's try this again. Wow, acetic acid, you failed me. All right, so Vaughn's going to grab us some more.
Stronger
5%?
Huh?
5%?
Let's see, this is 0.5, so whatever the next strongest is. There weren't too many options. All right, I'm surprised that's not lighting up. All right, now we'll have to do a calculation later in like second or third term to figure out how many ions we had disassociated.
Isn't most like household white vinegars like 3% or 5%?
Yeah, I think that was just, I guess it was too weak. All right.
I didn't know that you could purchase it so diluted.
Yeah, well, they probably made it more dilute, but I was still surprised it didn't light it up. there's sugar. So after you copy sugar, we'll look at acetic acid more and what was supposed to happen, or what will happen. All right, so let's look at acetic acid for a second while we wait to get stronger acetic acid. And so now this kind of goes back to some of our resonance structures. And so we have what's called here an acidic proton. And so we also have kind of this class of chemicals called organic acids. And of course, acids can also fall into this category. So I could have brought like hydrochloric acid, and that would not have given us issues with the light bulb. And so let's look at these acids. And so in the case of our acetic acid, well, let's back up for a second. So let's look at the most simple process. And so that's going to be the auto-ionization of water. And so the other thing is, right, again, we said water's just kind of sitting there. There's not a lot going on, but there is still a small amount of ions in solution. And so this goes into pH, but all we need to know is that even in neutral water, there's still going to be some H+ ions and some hydroxide. And so what happens is, you have two water molecules staring at each other, and then some small percentage of them, and again, watch how I'm doing this attack, so action starts at the electron, and then we go, it wants to pick up a hydrogen, because again, this is a pretty polar bond, and so oxygen has a lot of that electron density, and then of course, the electrons in that bond go to oxygen, and then that leaves us with formally hydronium here. And so if you notice too, chemists really just use H+ and hydronium interchangeably, so you never truly have like a naked H+ ion floating around in solution. It's either going to be hydronium, or of course, you also make hydroxide as well. So that's one simple process. And so if we take this with our vinegar,
Got 4 molar and 20%.
cool.
20%, that's so much.
All right, so let's go back to this so we can actually see this happen.
It's 17.4 molar.
No, it wouldn't be that high.
You sure?
Yeah.
Maybe I read the chart wrong.
Okay, dumping that. All right, let's try.
Wait, do you want to do the camera for the live stream people again?
Oh, yeah. Well, I forgot it for you guys, too. I do have it on. Oh, no! This stupid OBS keeps failing me when I switch cameras and scenes.
Oh, there we go.
Okay. So let's try, I'll try the 20%. Now I hope I can reach it. Yay! Woo! All right, that was almost anticlimactic.
But it still lights up.
But it lights up, but that does tell us, so later, now we have to look up how much electrical ions in solution you actually need to light up a light bulb or do some calculation like that. I'm sure we can do the math somehow. And so even then, it was still kind of a weak light, which is kind of interesting. But that's also just telling us some more stuff. And so what's going on in solution? Oops, let me go back to here. So we have our acidic proton, so that means it's susceptible to attack. And so again, right in solution, we have our water comes up. And then I'm going to use this arrow since it's in equilibrium. And so we can see that because of how weak the light was. And so this is what's called a weak acid, in that it does not fully dissociate, but some of it does. So some of it does react and dissociate to form our acetate ion. And you should have acetate on your polyatomic chart. So it has that funny name of like COOH and CHO, and it has different forms depending on what chart you're looking at. Yeah, so sometimes it's C2H3O2H is some forms, or like CHO. You see some weird stuff. Do y'all know what I'm talking about?
Is there supposed to be something in between, like all the lines right there, right next to the carbon?
Hang on, let me fix this hydrogen. And then which lines?
Like where the oxygens are connected?
Oh, this line? Oh, this is a carbon. Sorry. So does everybody know that that's a carbon? I kind of use the... So this is a carbon center here.
Like in the sugar molecule picture that you took, all of the corners are.
Yeah, so all
carbons,
of
right?
these are carbons as well. So and so that's something you have to get used to with the organic chemists. I always use that shorthand, so every line or point is a carbon. Hydrogens are not drawn on the carbon explicitly. But it's this ion formation, and then of course we would get hydronium ion as well. So those ions floating around in solution are of course what made the light bulb light up weakly. And again, we'll come back to these concepts later when we hit kind of acids again, and then we're going to see acids again, especially weak acids with the dissociation constant. I can't speak. But we'll kind of do more math with that, so you'll actually, set up some algebraic equations and solve that. So we're not going to quantify it right now. And then just kind of on a side note, and well, let's look at this. And so this little picture, again, all that's saying is we don't really have that. It's just going to automatically form our hydronium. But again, chemists are generally lazy, so they probably just write H+. They won't bother to write out hydronium. And so this is just another drawing of acetic acid. And again, note those equilibrium arrows, so showing it's going to go back and forth. And so that's the key thing with kind of the weak acids, and later we'll see with the weak bases, is again, they go back and forth. And so let's talk about some of these other acids then, and how they differ. And so we have a mix up here. And so hydrochloric acid, for example, this is considered a strong acid. And whether it's strong or weak, so that has nothing to do with whether it's dangerous or not. So it's really just, does it fully dissociate? That's all that question is saying. And so if we look at HCl, it's called a strong acid because in solution we would use a single-headed arrow to show that it fully disassociates. And I won't make Vaughn take another trip to the stockroom, but had I been thinking better, I would have brought a strong acid as well to kind of show. If you want to. Only if you're feeling really motivated, but bring like a lower molarity, so probably like 1 molar or less. of HCl.
I'm getting my steps into it. Let's go.
I'm sorry, this is why I don't do demos. We'll bring the whole lab down.
I don't see a problem with that.
Is there a way to tell off the bat whether it's a strong or a weak acid by its chemical formula, or is it?
It's more just like, hey, you learn these are the strong acids. Yeah, so there's like the 7 strong acids. So you have hydrochloric. Nitric is another strong acid. Sulfuric, the first dissociation would be strong, and then there would be some sort of dissociation constant for the second, since this is called a diprotic acid, since it has 2 protons. And then acetic acid, so that's weak. Citric acid, that's probably weak because it's an organic acid, so I'm just kind of judging. So citric acid, I'll just pull up a picture of citric acid. That one's kind of acute structure. So that's citric acid, and then of course, right, this is super useful in food production. This is also what we have in lab, right, the citric acid powder. And so it comes in different forms of different salts as well. Just trying to find, because it can come as like a trisodium version as well, and disodium. Yeah, and of course that's what gives, you know, the citrus fruits its flavor, or like those lemonade packets, those have citric acid. Did you guys get any Zotz candy from upstairs? That had citric acid in it. So that's, all the candy is basically citric acid. So I'll put a lot of candy production. So carbonic acid, so this is weak. And so that's all equilibrium systems. HF, so this is interesting because HF is super dangerous, right? You would not want to get it on you. But it's still considered a weak acid. So just because of, again, the equilibrium.
Oh, is it because fluoride is more like pulling the electrons in water?
Maybe. I'm actually not sure why it's weak, but I mean, part of why it's weak is, again, that it has a tendency to go back.
I actually have a funny story about this hydrochloric acid.
Oh,
If
man.
you want to hear.
Yeah, while I pour this, you can share a funny story, and then we'll go back to HF, too.
Tell us about your hydrochloric acid.
So me and Declan, I was replenishing all of our molarities of hydrochloric because we make them in-house. And I was working on 1 molar, and I was taking our 6 molar bottle and diluting it instead of just grabbing the glacial. And I was doing it in the fume hood, and just, I had made the solution, I had done everything right, and then I took the funnel, not checking the label, and poured it back into the 6 molar bottle.
Oh, no.
So me and Declan then had to do some analytical chem to
Figure out how many moles you had.
what the molarity we actually had, and we figured it out. It was just was like, this is a stupid.
One moment of weakness.
Just 1 moment. Check your labels on your chem bottles before you pour stuff back into them.
Yeah, reading labels and reading labels is always good. All right, we have vinegar there. Oops, I know I did it again. So let's continue talking about HF. So there's a good point into how you know it's a weak acid, and so this is kind of also like you've got to be careful of what you're mixing. And so, for example, sometimes people, you know, use like sodium fluoride or other reagents, but then what you have to be careful of is that you don't generate, right, fluorine or fluoride waste. So anytime you have fluoride ions in your waste, right, that means that they're literally reacting then. So then let's write out the mechanism. And so, right, you have your fluorine or your fluoride ion, and right, obviously very electronegative and upset. And so then it sees water, and then it's going to pluck off, right, hydrogen here, reform HF, and then also make hydroxide in solution. So you have to be careful with your waste and what you're making, and because this is a big danger in chemistry sometimes, is you don't want to be generating HF in your waste. All right, let's look at this demo now to compare. So we're trying to show that HCl is a nice strong acid. And so we have this 1 molar, which I'm now pouring into the improperly labeled vinegar container. Let's get this out of the way. I'll try. Okay. And so now let's see how bright. Woo! And so right, that's a whole lot brighter even compared to our vinegar. And so again, right, even though it's just 1 molar, all those ions are disassociated. So that's why I was saying, right,
So
we'd...
it was like the same brightness as the salt water. Is that because it fully disassociates like water? Like salt doesn't?
Yeah. And so that's part of it, is all that brightness. So now I'll go back. And so now we could see, okay, that kind of explains why HCl is a strong acid. Again, fully disassociated, so 1 mole of hydrogen ions, 1 mole of chlorine ions. So we really had 2 moles of ions in that solution. And of course, later, so we'll save the math, but eventually we will calculate the math of how many ions were in this solution. I just want to save it for either second or third quarter, I don't remember.
So is it just the acid that conducts electricity, or did you dissolve it?
So it's just the acid. So it is in water, right, as a dilution. So it's reacting. So you have to remember, right, it's still reacting with that acid, or sorry, with the water, right? It's just now it fully disassociates. So again, in the case, so let's just think about HCl, what's really going on instantly, right? You have your HCl, you drop it into solution though, and so instantaneously, since it's going to disassociate, all of those hydrogens will be picked up by a water, right, all forming hydronium. And then, of course, making our hydroxide and leaving chloride ions floating around as well.
Can you show us the hydrofluoric acid, how it dissolves as well? 'Cause that,
So this
wouldn't
is-
there be 3 hydrogen?
Well, this is the reverse. So I just showed fluoride making HF, but then we can go the other way as well. So, right, we can see how HF disassociates, but again, it doesn't fully disassociate. So that's where we have to put the equilibrium arrows. And then now it makes hydronium. Phoenix, did you have a follow-up?
So if there was just straight acid and nothing else, would it not conduct electricity?
Well, acids, like it still has to be in some medium. So that's kind of the definition of an acid.
Okay. What is acid without that? Like by itself, is that called something else?
No, because even like strong acid, it's still a solution. Like it's just really, really pure and concentrated. Yeah.
So you can never have like 100% acid?
Well, I mean, it's like, yeah, it's like 12 molar is considered glacial acetic acid. And then there can be organic salt or like organic acids that are solids. And like those would not conduct electricity. And there could also be like the liquid ion salts though, so those would conduct electricity. So it kind of depends what state it's in, of course. Yeah.
So in this experiment, we saw that like water wasn't very conductive. Why isn't like shows and stuff that we see like a live wire just like lighting up a pool of water really easily?
Because it still does, right? So there still are ions in solution. So that's where you can still get electrocuted. It's just that on this case, so that's what I was saying right now, we have to figure out, well, what's the rate? How many ions do we need in solution to light up that light bulb? Because, you know, obviously there's some threshold. But yeah, it still is conductive since it does auto-ionize. And still have other ions, salts. And so one thing, if we could, go test around like all the drinking water, see if we can get it to light up or not as well. So depending like how hard your water is, like maybe we could get it to light up. That all depends. All right, so we covered acids, and I think we already hit this at another page. And then, so this is just basic properties of acids and bases. So acids, and you probably know this from experience, they tend to taste sour, limes, lemons, all that good stuff. And then we'll come back to this later, but we are kind of seeing they make these hydronium ions, or H+, and then obviously they neutralize bases, and we'll kind of look at this reaction in the double displacement. And obviously we've seen them react with metals. And then bases, I don't know how many people have tasted bases. I don't know if people still get their mouth washed out with soap.
I did.
Oh no. So you know what that base feels like, a little bitter, they're kind of slippery. And then they produce hydroxide ions and obviously neutralize acids. All right, so now we kind of touched on the double displacement. So now let's look at double displacement next. I think that was next. And so we're looking at double displacement reactions. So let's try this out. And so let's do this, because really what we're asking is, well, what drives this reaction forward? What causes it to react? And so now let's look at I do need a producer, apparently. All right, so now our next demo. Let me unplug the other thing before I electrocute myself. And so now we have our test tube here. And let's label it so we don't have mystery liquids. And so what I'm going to put in there is I have our silver nitrate. So I'm really doing the reaction that was on our slide. Then I'm going to add to it sodium chloride. And, oh, we can't see the bottom of the test tube. I guess I'll just hold it. I think
Assistant.
I'll be okay.
Or if you turn the rack like a quarter turn, it'll be easy. Yeah.
Can you see that? I can't tell if y'all can see.
Yeah, we can see the bottom of the tube.
Okay. I was trying to make it, I don't know if that helps. Oops. All right, so now let's add, so that was our sodium hydroxide. So now let's see what happens when we add silver.
Ooh.
And so do we see that get?
It's white.
So now it's nice and white and cloudy. And so let's look at that. So that was what we were looking at on our screen here. So I'll keep the slide cam up. And so we just did this reaction. And so yes, that is what happened.
So it's the silver chloride that makes the white cloudiness?
Exactly. And so now we'll kind of do another reaction in a second. And we'll look at these rules because that will kind of explain to us what's going on. But yes, so the key part of that reaction is that we had to have some sort of a precipitate formation. And so that has to drive the reaction forward. Or the other way to drive a double displacement reaction would be a neutralization. And so I didn't bring one. It's hard, again, hard to bring the whole lab. But right, a neutralization is also a double displacement. And of course, the general form of our double displacement is we're just swapping our cations. So now A goes with D and C with B. So make sure, right, you have a cation with an anion. So that should be consistent. So now we can do the same thing with our neutralization. So swapping partners, we form sodium chloride and water. And so this is the other key point, is that we either have to form a precipitate or we have to form water. So those are the two conditions that drive a double displacement reaction forward. And so now let's go back to the big can and kind of see what we mean by that, by driving a reaction forward. And so let's try another scenario. So that one was cool. And so now let's try, so let me put my silver nitrate away. So I'll use sodium chloride again.
Is sodium nitrate actually clear?
Sodium nitrate?
Or no, sorry, silver. Or so the silver chloride, whatever you had the other bottle.
The silver nitrate?
Yeah, silver nitrate.
Yeah, silver nitrate's an aqueous solution. It's pretty clear by itself. And then, yeah, sodium chloride is just a clear, colorless. And then, so now I'm going to add to it lithium chloride. And let's see what happens. Nothing happening. So how come nothing's happening? What's going on?
Are they more stable in the way, in their ingredient forms?
Sorry, what two compounds were we adding here again?
So what two compounds were we adding? So let's look at that. And so we added together, and I lost my pen again. So we added lithium chloride plus sodium chloride, and then we seem to get no reaction. So what happened?
There's not a difference between, they both have the same anion, so they're both still going to be completely
Even if they do
disassociated
switch,
water.
they don't change form.
Yeah, it's technically not even a switch because it's just lithium ions and sodium ions mixed in with chlorine ions.
That makes sense.
Exactly. And so we could, I picked an easy one where they were kind of the same ions, but we could have done this with another chemical like sodium nitrate. I guess potassium nitrate would have been another good pick. And so Vaughn was on the right track, and let's look at that further, right? So what you're kind of seeing, well, what happens when we swap them? And then what you really want to ask as well is, so what's a new compound? And then is it soluble or insoluble? So that's where all these solubility rules come in. And so now we have kind of these rules, and now we can kind of see, oh, this is how we make these predictions. And so let's look at a couple of these, and then we will talk about kind of caveats and how we'll explore this further. So this is really just our first kind of cursory look at these solubility rules. So this is kind of maybe more high school chem that you've seen this before. And so we can see lithium, sodium, potassium, ammonium, these all tend to be soluble. And so if you kind of think back to lab, like, oh yeah, we do use a lot of these ions, and so you can see they don't have any exceptions. So same thing with nitrate. So that's also why we use a lot of nitrates in lab. So they tend to all be soluble. So like iron nitrates when we add them. Acetates as well, those are all soluble. So no exceptions. And then of course, if we think back to the one that did form a precipitate, so our sodium chloride plus silver nitrate. And so again, we kind of have to think about, well, in our beaker, what were the possible combinations? And so I kind of like to think about our beaker. And so there's our beaker there, so sodium chloride, right, silver, and nitrate. And again, just like we did, we kind of see what are our new combinations. So these are two new possibilities. But then if we look up sodium nitrate, well, those were all soluble from our rules. So yes, it had to be the silver chloride, which if we look, so chloride, bromide, iodide, so those are insoluble with silver, mercury, and lead, so those kind of heavy metal ones.
So then the silver chloride would be the precipitate that falls out of the solution?
Yep, and so that's also why it was denoted with the S there, so S saying that it's coming out of solution as a precipitate, as opposed to, right, the AQ designation, which means it's dissolved. And so let's kind of talk about where we're going to go, though, and why some of these rules seem ambiguous. And so you could find discrepancies. You can, this also says, so like you have sulfate and strontium, barium, lead, silver, and calcium, but sometimes you see like calcium is slightly soluble, and there's all these like slightlys, and sometimes if you find a different chart, it may not agree. And so why is that? And so that's because we're going to take a deeper look later. And so let's go back to silver chloride, since we're somewhat familiar with it. And so what we really will get at later in the course is what we are interested in truly to figure out how much is in solution is the solubility product constant, so KSP. So later in the course, again, second, third quarter is when this all starts to happen, is we'll actually quantify this and see, you know, how much is actually in solution, because yes, there's a small amount in solution, but obviously when we overwhelmed it, like we did in this reaction case, you know, it starts crashing out. And so we'll take a much deeper look at that later, but that's where you get kind of the discrepancies in the rules and why it says like slightly or somewhat soluble. And so all that is because of that. And so then just take in other exceptions. So I'll probably bring a printout next week, or in lab I might have a few. I just didn't get around to it. But we can see hydroxides. They tend to be insoluble unless, of course, they pair with our alkali metals here, and then alkaline earth. Some of these are also soluble. And then look at hydroxide. This is, again, where you see a lot of discrepancies on what is soluble. And so sometimes, you know, calcium hydroxide is considered more soluble. But again, we'll look at the details and really understand later once we are able to quantify it.
So if something is labeled as being slightly soluble, is that when you would use the like equilibrium one, because it could go back and forth?
Yeah. And well, all these solubilities do have some sort of equilibrium, right? It's just a question of how much, but that's where we'll get into like more of the quantifying it later. But I at least want to explain like why these rules sound ambiguous. And then you're kind of seeing, you know, because we asked a lot of good questions, because all this goes back to like our crystal structure, lattice energy, right? And so you asked a lot of good questions before of like, how do we know what's soluble, what's insoluble? But unfortunately, it really does come down to experiments still. So we can make all these predictions, right? We can calculate the charge, but we still experiment to see, you know, what is stronger, the solute interactions, so the compound itself, or those solvent-solute interactions and how that works. So, yeah, interesting that y'all have been asking good questions too. All right, we're kind of running out of time. So we saw acid-base was a double displacement. And the last thing that we didn't talk about was oxidation reduction reactions, which we could talk a lot in detail of. And so we'll have to visit this next week. So blah, 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 blah. Let's skip down to kind of the rules for signing oxidation states. Because these rules are key, and then we can go back and kind of analyze what's an oxidation reduction reaction. And so first we have to know how to assign oxidation states. And so the number one rule is that free elements have an oxidation state of 0. So like star this, plaster it somewhere, burn this into your brain. But anytime you see something in its elemental form, it's 0. So that can be, right, sodium metal, chlorine gas, so don't forget all your diatomics. So H2, that's still elemental form. S8, that's elemental form. You know, P4, elemental form. So that's the first step. And then rule number 2 is all our ions still have the same oxidation state as our charge. And this does try to give you the distinction. So, right, our ionic compounds, those have discrete charges that we can measure. Those are equal to their oxidation state. When we get into covalent compounds, it becomes more bookkeeping-ish. But, of course, you can still follow the pattern on your periodic table. And then we've seen this before. The sum of all the oxidation states in an atom has to equal the compound. Usually it's 0. And so then the other thing is, well, we have to base our oxidation states kind of on the other atoms going in this order. And so these are the priorities. And so fluorine is always in a -1 oxidation state, and it's at the top, so it takes priority. Hydrogen then is next, and it's usually 1+, unless we see it's in a hydride. So like aluminum hydride, so that would be an example. So these metal hydrides, that's the only exception for hydrogen. Otherwise, it's 1+. And then our other one to base stuff off on is oxygen. And so oxygen is always -2 unless it's a peroxide. So peroxide is when you have this O, single bond O, and then it's bound to any other thing. So obviously the simplest is hydrogen peroxide, but you can have a wide library endlessly of organic peroxides, hence why I just put R. That just means anything. But a peroxide is like this, so each oxygen is then -1. So that's the only exception. And then it follows how you expect, right? Group 7 is always -1, group 6, -2, group 5, -3. And so note, again, your polyatomics, this is when we can have like formally positive oxidation states. And so again, you base it off of the oxygen. So in nitrate, that's how nitrogen ends up with a +5 oxidation state formally. All right, so we might have to stop here. So we'll pick up back here on Tuesday. But we'll kind of, where we're going, so we want to look back at double displacements. And we'll find that they are actually not redox. So we'll look at that. And then we'll see how the single replacements, those are always redox. And then we'll look at, of course, other scenarios as well. So you can probably tell, right, combustion, those are also redox. But I don't want to rush this, so we'll have to, again, revisit our oxidation reduction. So we'll hold off on that. So we'll go into more detail on Tuesday. And so we'll take our 10-minute break, and then I have your quiz for this week. So I'll go ahead and stop the stream, and then if you want the quiz emailed to you, if you're online, just send me an email so I know.